Hello friends, today we are going to discuss one of the important technique in genetic engineering, DNA sequencing. DNA sequencing. You know, DNA sequencing plays an essential role in understanding the function of genes or inheritance of genetic disorders or gene manipulations, DNA cloning, all these essential steps, all these different ways of biotechnology depends on DNA sequencing. Because, for example, say a function of gene, you have to know the function of gene, you have to understand the sequence, what exactly it is. Are there any manipulation? That means are there any defector genes in the way of mismatch like that? So the entire basic concept of this depends on DNA sequencing. There are three ways that a DNA can be sequenced. The most old and conventional approach, Maxem Gilbert, and the current dideoxynucleotide method, and the advanced automated sequencing. You know, Maxem Gilbert, dideoxynucleotide, then automated DNA sequencing. Automated sequencing. The first one, Maxem Gilbert. This technique is completely based on chemical reagents and reactivity. Then Maxem Gilbert, for the first time in 1977, worked out this technique for the DNA sequencing, and this completely depends on chemical reagents. Chemical reagents in the sense, say a one particular chemical reagent will break down one particular base. Dimethyl sulfate DMS, for example. That means DMS targets G residues, or X residue targets X chemical targets Y residue. That means based on this logic, they have established a technique for DNA sequencing. It is called Maxem Gilbert and completely depends on chemical reagents. And here the one more important thing is radio labeling. Say P32 is the most common radio used radioactive isotopes for identification, because later onwards you have to electrophoresize, then autoradiography. That means the bands, that means electrophoretic bands has to be analyzed with the help of autoradiography, and for that this radio labeling is must and should. Just like we were discussed in previous classes, that means say RFLP analysis, blotting techniques, in all these things radioactivity is very much important. That because you have to electrophoresis, then autoradiography. The same concept here also, but in different way. Here the mechanism involves, for example, say the source DNA. It is a source DNA. We radio labeling with the help of P32 at one end, so that this will be used as a template later onwards. As a template. This is source, and after this we have to distribute this template, that means the basic DNA strand, into 4 reaction vessels. Here it is named as G. This is A plus G. This is T plus C. This is C. I told you already, there are chemicals specific for residues. For example, dimethyl sulfate for guanosine, for G residues. We are not going to the deep. This template will be distributed, after the cleavage. What exactly happens here? Say we have radio labeled one of the strand, that means which we consider as a template strand, and this template strand has been distributed along among the 4 reaction vessels, I mean the test tubes, and after that we have to add certain chemicals which specifically digest the DNA fragments at a particular location. For example, I told you DMS. Yeah, we are not going to discuss about different chemicals and be in it. Just that means not we are going to discuss about the chemical mechanism, but there are certain chemicals. Just simply understand certain chemicals that can break down the DNA fragments at particular locations based on their specificity. Specificity means just like DMS targets G and some other chemicals targets other residues as well. That leads to breakdowning of the targeted, which is a radio labeled DNA fragment, into small fragments. Say for example, G means here it acts on G residues. That means say the DNA strand, the template strand contains guanosines and this particular chemical acts on G. Then another one, adenine, actually it mainly targets on adenine residues, occasionally guanosine as well. That means G residue as well. Then thymine, then C, then cytosine. When it specifically acts on this residue, it will break down the DNA into smaller fragments. Then what happens next? When it breaks down, then when it breaks down, it leads to formation of different lengths. The next step, we can continue here. Formation of different length DNA. How? For example, consider a DNA fragment, say with respect to C, that means cytosine residues, at 4th, at 7th, at 10th, there are C residues. A particular chemical specific to acts at R4 or 7 or 10. That means there are possibility of different combinations. Assume a strand with C residues at 4th position, or else a strand with C residue at 7th position, or else a strand with C residue at 10th position, and it leads to different lengths. For example, if it breaks at here, it leads to 3 bases. That means a tiny fragment of 3 bases. Here 6 bases. Here 9 bases. What is 3, 6, 9? And how we can determine the length of the fragment? It depends on its distance from the radio labeling. I told you already. That is that means the P32 at the 5' end, its distance from the radio labeling determines the length of fragments. This is very important. So, for example, higher the distance from the radio labeling, and according to the fragment size will be. So it depends on that completely with respect to the distance from the radio labeling, according to the different varying fragments in 4 tubes. The test tube 1 with G, the second with A plus G, the third with T plus C, the fourth with C. So different test tubes may have the different length of DNA fragments because of this logic. Because it specifically acts on specific chemicals, that means specific residues. Then after that, the next step is we subject the same to gel electrophoresis. We already knew that electrophoresis separation side by side. Say for instance, after the electrophoresis, you establish this autoradiography. Say that means after electrophoresis, it's a usual procedure, electrophoresis. Say you have to run the gel either to agarose or pollock element. Pollock element is most accurate than gel. Then after that, then you develop the electrophoretic plates, and with the help of autoradiography, that means through autoradiographs, we have to identify that. That means determination of DNA sequence. How? Say for example, say different bands. Say it's a complementary sequence. We have to read from bottom. Say C. With respect to this, we have to act. G, A plus G, T plus C, then C. Here longer fragment to shorter. This is very important. You know, we knew that in electrophoresis the small fragments move farther. They move down to the plate. Whereas longer fragments at the end, at the beginning. So it's the same sequence we have to apply here, okay? Accordingly, we have to get, say, for example, C, T, G, A, T, C, G, C. Okay. How we have to establish, you know? Say C, then T, then G, then A, then T, then C, then G, then C. It's a complementary sequence. It's a complementary sequence with respect to the DNS target DNA sequence. Okay, these are bands, you know, electrophoretic bands. Electrophoretic bands. Say the test tube G with G residues A plus G T plus C. We have the same. We have to run on the gel side by side. Accordingly, they will develop a specific band pattern. I told you already. The smaller fragments they move farther. Then, with the help of automated technique, what we call automated graphs, we have to determine the sequence based on this technique. That means that means it is very easy to understand. The smaller the fragments, they move at the end according to the complementary sequence. That means the automated graph will be developed. So it's about Maxem Gilbert sequencing. And the most important one that currently we are following is dideoxy sequencing. Dideoxy sequencing, simply before we go into the topic, we have to understand certain basics. Deoxynucleotides. We have to understand the terminology. Deoxy. At two specific locations, there is no hydroxyl group. In general, in DNA, the kind of ribose sugar we have is 2-deoxyribose. That means at second position, that means at second carbon, there is no hydroxyl group. Say, for example, for understanding, say these are the bases, either A or T, C, G, and they combine with a D-ribose. At second position, there will be no hydroxyl group. This is fifth, this is second, this is third. There will be no hydroxyl group. That means this is 2-deoxy-2-D-ribose. At second position, no hydroxyl group. Say here dideoxyribose, dideoxyribose. That means dideoxynucleotide. It leads to how it ends. Say this is a ribose. At second position, this is usual HH, and third position also. There will be no hydroxyl group. This is very important. These are the bases. Say ATCG. Just see the distinction. Third carbon and second carbon. That means both at C2 and C3 no OH groups, but here just C2, no OH. That is why dideoxynucleotides, because in the ribose, that means in the deoxyribose, along with the second carbon, the third carbon also lacks hydroxyl group. That is why it is known as dideoxy. So because understanding the basic stereochemistry, means the organic chemistry of the compound, is essential in understanding this technique, because the relevance, the interdependence of the mechanism depends on this particular third group, lack of hydroxyl group. You know how I will tell you. So it's about the basic issues. And regarding the other issues, dideoxynucleotide method developed by Frederick Sanger in 1980. You know, he is the only person, as far as my knowledge goes, who won Nobel Prize twice in the field of medicine. Like, for first time he got Nobel Prize for insulin, and the second time for nucleotide sequence of a RNA, a viral RNA. And he has designed this technique, and they currently are following them. And what is the basic mechanism of dideoxy? In just we have to discuss before we will get into the schematic presentation how this process works well. We know that DNA replication, we already discussed in the previous classes how it works. Say a prokaryotic DNA replication, or even eukaryotic. One strand is called leading strand, the other one is called lagging strand. For example, in case of eukaryotes, the leading strand shall be synthesized by DNA polymerase delta, whereas in case of lagging strand, DNA polymerase epsilon. Whereas in case of prokaryotes, it's a different scenario. There is no such distinction like alpha, beta, DNA polymerase alpha, beta, delta, gamma. There are only three kinds of polymerase: DNA polymerase 1, 2, and 3. Here, DNA polymerase 3 will involve in synthesis of replication, that means a DNA. So it's okay. And what exactly happens in DNA replication? Simply the raw materials, deoxyribonucleotides, DATP, DCTP, DGDP, DDDP will be added as a raw material, and simply the DNA polymerase will add, and then the esterification. That's esterification where, that means existing fifth carbon, that means 5 prime, with that of the incoming 3 carbon. That means phosphodiester bond at fifth and third carbons. Likewise, the DNA polymerase chain will be established, what we call phosphodiester backbone, or simply phosphate backbone. This is about the basic issues of DNA replication. Why and how it has been formed, and what makes the DNA polymerase growing chain to extend uninterruptedly, at least on leading strand. Because there is a point here, the third carbon have hydroxyl group. Third carbon has hydroxyl group. This is very important. Third carbon has hydroxyl group. Since it has hydroxyl group with third carbon, it participates in the esterification, phosphodiester bond. This is how just a tiny organic nature of deoxyribose, it plays an important role in entire construction of our life. And whereas in case of 2-deoxyribose, dideoxyribose, there will be no hydroxyl group at third carbon as well. Since there is no hydroxyl group at the third carbon, there is no possibility of chain extension. Simply the chain gets terminated, no matter whether it is the leading or the lagging strand. No matter whether there is a DNA epsilon or delta or DNA polymerase 3, simply the chain will get terminated because of lack of hydroxyl group at third carbon. This is the basic reason, and this is the crux point for entire scenario. This is become like how, for example, like we have, let's pick up a DNA template of interest. I will tell you how it runs, okay? After that, primer we add, we knew that. Say this is 3 prime, 3 prime. Okay, primer, this is primer. After this, the raw materials, DATPs, DGDPs, DCTPs, and DTTPs. Distribute in four vessels. Okay. So distribute the template DNA along with primer in this vessel 1, 2, 3, and 4. You add all the DATPs here. Add all the raw materials here. Okay. Then add the polymerase, clino polymerase. Now we are using Taq polymerase, Thermus aquaticus, a thermophilic bacteria. The DNA polymerase the same has been using in this activity, no, in this biological process. Okay, for not lipino polymerase. That means we have added the template, the raw materials, the primer, what we call primer DNA, simply called. It's called primer DNA. And then the DNA polymerase. DNA polymerase. Okay. In all the 4 tests, 1, 2, 3 and 4, this is enough for synthesis of DNA. That means, okay. Then we have to add specific, important, specialized, because it is called chemically prepared. Dideoxynucleotides are not naturally present. They are chemical. That means synthetic nucleotides. Dideoxy ATP, dideoxy CTP, dideoxy GTP, and dideoxy TTP. Simply DDA, DDC, DDG, and DDT. This is how they should. Then we have to add one here and one here. That means DATP here, DCTP here, DGTP here, DTTP here. That means along with the basic requirements which facilitates the DNA replication, we should also add the dideoxynucleotides, each 1, 2, 3, 4 respectively. You know what happens? For example, take number 1, test tube number 1, and this will be the template strand, the primer, the DNA growing chain will continues as usual till say DATP, DDATP will come into the action. If it comes here, it will terminate the chain. Anytime it may come. For example, say primer, I will tell you what exactly it is, plus 4, that means after 3 bases, or primer plus 7, that means after 6 bases. Anytime it may incorporate, when the dideoxynucleotide, either it is DC, DG, DT, that means adenine, CC, ADC tissues, okay, came into existence, the chain will get terminated. The same action on the rest of the 4. That means rest of the 3. That means it all together will create DNA fragments of varying lengths. Will create DNA fragments in all the vessels of varying lengths. I will tell you how the issue is, okay. When the rest of the process same. After we get the different DNA fragment, that means then the denaturation will be done, and the most important here, of course, the usual process, the P32. P32 we have to label either to the primer or to the dideoxynucleotides. Therefore, after labeling, the process will be done like this. Then, after this denaturation, the free strands which are radio labeled we can collect. Then electrophoresis, then autoradiography. But this is not as simple as I have explained. There will be a technique to understand and to determine the sequence. Okay, the process is same. Electrophoresis and through autoradiography we can determine the sequence. How we have to determine the sequence is very important. So it's about the basic working mechanism of dideoxynucleotide sequence. Okay, I told you already. When the dideoxynucleotide come into action, the chain termination will be done. That is why it is otherwise called chain termination method. Chain termination method. Say for instance, this is dideoxynucleotide. Say DDATP, DDCTP, DDGTP, DDCTP. Then this is primer with nucleotide. Then primer with nucleotide sequence. and how it will come, how it has been come. Say this will be the template DNA. And this is the parent, this is the what's complementary. So this is primer and this is new DNA. Here we have to this is very important point. Okay, then for example DDETAP, that means deoxyadenine, that means deoxy a residue. When it come into action, the chain will get detonated. The complementary base pairing is T. For example, here the T is here. That means after 1, 2, 3, 4, primer plus 4. One more for understanding. And another possibility, after 1, 2, 3, 4, 5, 6, 7, 8, 9. That means primer plus 9. The respective sequence will be like this, G, C, C, then DDA. Then primer, that means the corresponding sequence I am giving. This is primer plus G, C, C, DDA. Opposite to T, the complementarity. DDA, the chain detonated. The same here also. Plus 9. Another T will come here. That means the residue will be like G, C, C, A, G, T, C, T, then DDA. Then take another example. With respect to dideoxy cytosine, say that means plus 2. Primer plus 2. Because the opposite strand, for convenience we will write here G, C, C, A, G, T, C, T, A. This should be the opposite strand. Because since CT becomes, where it will come? On the second length itself. Because the complementary is G. At the same time, another one, say for understanding, we can shuffle here. G. C, then C, then G. Okay. That means another G will be there here. The opposite will be 1, 2, 3, 4, 5, 6, 7. Primer plus 7. Because at 7th position G will be there. The complementary to G will be C, but here it is DDCT. That's why primer 7. The corresponding sequence will be like, say for here it will simply C and DDCTP. Whereas for here it is a G, C, C, A, G, T, and DDATP. This is very important. Then for DDGDP, primer plus 1. Primer plus 1. That means the first base itself, DDGDP. Then one more time it will come. 1, 2, the opposite will be the DD primer plus 3. Then one more time it may come plus 4 plus 5. That means according to the sequence will be G, G, C, D, D, G, T, P. This is 1, and for plus 5 this is C, so G, C, G, A, and DDGTP. Then the last one, DDCTP, DDTP. Sorry. Its complementary sequence is A. 1, 2, 3, 4, 5, 6. That means primer plus 6. One more time. 1, 2, 3, 4, 5, 6, 7, 8. Primer plus 8. According to the sequence will be G, C, C, here you have to change GCC, G, A, G, T, C, T, A, C. Same here, G, C, C, A, G, 4, 5, then D, T, 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 P at 6th position. Then again same, G, C, C, G, C, C, G, C, C, then G, G, C, this is G, G, then C, 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 then A, G, T, C, then D, 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 P. The same, the entire thing simply depend on one concept. The primer, then the polymerase will add upon the DATPs. That means deoxyadenosine triphosphate, DATP, DDC likewise. Unless its respect to termination dideoxynucleotide will come, the chain will get extended. Then when the dideoxynucleotide will come, the chain will get terminated. That is why as a simple representation of the primer, that means about the length, that means we can say to the extent of size. That's it. Later onwards get termination because of this. Say the same has been electrophoresized and auto radiography you have to develop. How we have to determine the complementary sequence is a very important point. Just like previous also, the larger to smaller, the same concept, TDATP, DDCTP, DDGTP and DDTTP. Conventionally, the band should be read from bottom to up. From bottom to up. Say 5' to 3'. How? For example, I told already G, 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 C, C, G, C, G, C, G. Perfect line, right? G, since we have modified again, G, C, G, A, G, T, C, T, A, C, G, C, G, A, G, T, C, T, A, C. This is a component and its respective bands. T, T, G, T, P, then C. Sometimes it has formed. Say G. That's 1. Then A. That means it's a basic illustration of how the banding pattern. That means it is complementary. It is, this is what we call stand. This is the exact determining sequence. That means with respect to the target sequence, it's complementary, and accordingly, this will be here. And from bottom to up, we have to study with respect to different bands. These are electrophoretic bands. This is how the issue ends. Corresponding to the kind of band pattern, you have to identify the respective complementary base. That is how you can determine the sequencing based on dideoxynucleotide. This is very much important because on an average 350 DNA fragment, that means size of the DNA fragment 350 base pairs will be determined by this method. Okay, the last one, the most advanced, which is what we get a modified version to dideoxy method. It's called automated DNA sequencing. Automated DNA sequencing is simple, of course in theory, but highly advanced. What we call automated DNA sequencing. What exactly happens here? Fluorescent tags will be added to dideoxy nucleotides. That's it. There are 4 different ways, 4 different dyes. And after that, electrophoresis, then fluorescence. Based on fluorescence, it will get recognized. How? The same concept. That means, say the DNA template strand, the primer, the substrate, that means the raw material like DATP, DCTPs, polymerase. Along with that, we will add a dideoxynucleotide which has been fluorescently tagged. You know what happens? When the dideoxynucleotide gets into the action, that means during chain termination, this fluorescent tag, say there are 4 different fluorescent dyes, will get incorporated into the DNA. This is very important. That means it is used as a carrier, a vehicle, just to get into the chain and terminate, and meanwhile it will also add. After that, the same concept with the help of page. For example, why we use page gel. Polyacrylamide gel electrophoresis is much accurate even in dideoxynucleotide method. Why we use page when compared to age? Because much accurate. Even it can recognize the differences among the DNAs at the rate of 1 base pair. High resolution when compared to the agarose. So, and here the same fluorescent will enables us to identify based on the electrophoretic bands. And this is very advanced thing. You may say the rate of on average 1 lakh base pairs. 1 lakh base pairs may be sequenced at the rate of even less than $0.2 per nucleotide. That means economical also, low cost and highly efficient technique. Say for example, a human genome project, for example, cellular genomics and others, even particularly cellular genomics, they have used this high powerful automated sequencing for construction of genome. That means nowadays, but the thing is, it's a bit costly and compared to the dideoxy. But conventional dideoxy is the best method. At the rate of 350 base pairs per day, you can sequence. So it's about for today's class. In next class we can discuss the other class.